All right, hi everyone. I just wanted to do one last video quickly, just to make sure that the ideas that were, I guess, put in the additional information for your project are coming through, and then just chat about a few more concepts that I think are important to know about. I think I've alluded to most of these, if not all of them, already throughout the class, but I just want to make sure that they're landing. So, actually, one of the things we definitely spoke about last time, um, when we were talking about responsible NLP, is mechanistic interpretability. Um, and the kind of one of the hallmarks of this mechanistic interpretability, what it was trying to understand is these things called the induction heads, and so this is one of my favorite slides of it. I'm not gonna maybe go through it again too much. I'm trying to be a little bit quick with this video, not to waste everyone's time. But there's the whole point of this is that like across two layers of attention, there was this like one mechanism that looked back into the context window and found a symbol that was had been referenced before, and then at the second layer of attention, you then kind of were able to attend back to now this retrieved bit of information and copy it across and use it as your output. So that's what's going on in this between these blue and these green arrows in this diagram here, and it's come. This is in the paper that I've cited at the bottom. The citation at the bottom is for the paper that did the mechanistic interpretability work on this. But I think the first thing I wanted to just mention about this is that like this is actually one of the primary reasons it's believed that like transformers in these large language models are actually scaling so efficiently is the fact that there is this emergence that happens from scale. And the induction here is one really good example about this, primarily because it does this thing called it goes through a phase transition. And so ultimately, what happens is that the model eventually learns that or realizes, again, anthropomorphizing a little bit, realizes that it cannot complete the task that it's been assigned based on the information that it has that's coming in just from the query. And so it starts to realize that there needs to be something else it can do using the other context that it's given. And in this case, it kind of just copies it out immediately. Now, that's also completely true of the project that you did, right? And you would have seen this and you would have kind of engaged with this idea when you were training your models on it, is you would have realized that the card you get input is meaningless. There's multiple classes that could be chosen, all of which could be valid for that card. And so what you need to really do is go and look back into the context window for the card that's going to kind of inform what category needs to be chosen, right? And so that's why I kind of picked this Wisconsin card sorting test, is because I think it demonstrates this like in context learning ability quite well. It's where in this case where there is this match between your present input and a prior instance that you've seen. Now, and this is again, I know it's something that you guys would have dealt with. It does happen reliably only from scale, and in this case, your card sorting test didn't happen. It didn't kind of have that necessary scale. Um, and the original paper here on in context learning is by Olson et al. I've cited at the bottom here. And they said that, well, have an argument that says that induction heads are the mechanism for the majority of in context learning. And so while this is really, really useful, I think these 2 points kind of go together in a way where it says, well, okay, induction heads are a very, very dominant, powerful ability for in-context learning, and in-context learning is very clearly something we want these models to use. But we also know that it comes from a phase transition and it's not a guaranteed thing. And again, you would have seen this in your projects. Like some of you did, you trained and you got 25% and your model was fine. Others, you got to like 90 or 100% or whatever it was. But your model trained and it's not super clear what exactly triggered that phase transition where it goes and says, well, oh, actually, I want to now start looking into the context window. And again, I think a lot of you then went and started feature engineering, and there were some really neat ideas around getting around it. So I think it was handled well in the project, and I hope that through that, that idea came through. But it's important to, I think the point that I really want to like hammer home here is that if this is what we're relying on, and there is this kind of unclear, unreliable phase transition, then this leaves open a whole bunch of very important implications for how we go forward in the field. And again, both these papers have now started to say, like, how do we bring this phase transition forward in time and things like that in training. But sometimes all you can just do is keep training the model and giving it more data. And that's ultimately where a lot of the field has gone. And a second thing that I think we should be taking away from this is a lot of the times when we hear like, oh, it's these are these models are just scaling, or it's just about throwing more data at the problem and stuff like that. I mean, it's not incorrect to say these things, but I think it's also there's a bit of nuance there because what it is emergence from scale and not just, hey, I just gave it more stuff and I saw what happened. And so I think a lot of what we're seeing now with these like neural scaling laws, I know you've heard of it, and again, here's the citation for a paper on this coming out of OpenAI. So they claim in this figure, they say, well, language model performance improves smoothly as we increase model size, dataset size, and the amount of compute used for training. For optimal performance, you need to do all three at once. And you can see there is this kind of like log scale on the x-axis, and then like whatever metric of loss of performance they have comes down in like this linear-ish scale. All right, and so again, it's important to note that this tends to be on a log scale. And again, it makes sense if what's happening is there's this like emergent strategy that is always kind of like accommodating the amount of compute and the amount of data that you're getting. So I don't think it's necessarily always just a case of more equals better in the sense that it's just more of the same strategy. There is actually a case to be made that with a sufficient amount of information and a sufficient amount of data, there is a phase transition that leads to entirely different behavior. And that phase transition is probably arguably what we're seeing more in these neuroscaling laws. Again, I don't have the answers to this. I don't think anyone has a full answer to this at the moment. But I think there's a subtlety there that can be missed. And again, it's something I've mentioned before, but a lot of people think that one of the reasons why large language models developed for language is because language follows a zip flaw or a zip distribution, where a lot of words are really, really common, and then most of them are uncommon. And again, there's a lot of them, and this immediately pushes it into this setting where the task is not achievable by just looking at words on its own. And if you are going to take that strategy, you're going to end up memorizing things based off of the few dominant, very frequent words. And so if you have difficult tasks and a lot of language that needs to be treated in that task, then pretty much the only viable strategy is to go through this phase transition and start using your in-context learning and start almost just copying information out of the context window based on what you have. And in linguistics, there's kind of like interesting ways of defining like names, because names are meaningless, right? Like the name Devon means nothing beyond the context that it's been introduced in, right? So, we all obviously know each other's names, and so our names provide, cue information for each of us about like the kind of person with that name or whatever. But that's only based on our own experiences, and that's completely personal in the sense that it's always in context. It's in the context of the other people, like Devon or named Devon that you've met, if you've met any, or it's just based on me. And so, it's always based on this in context kind of learning that we have, and that we're always kind of inferring back to in our in our own cognition. But it turns out these models eventually also land on that strategy. That then leads to a lot of questions around, obviously again, like we went through the responsible NLP and stuff like that, and we said that like these models are huge and there's lots of data that's needed, and that's not always true for low resource settings and stuff like that. So there are a few strategies, and I just want to name two. There's obviously more around how to get around this, and the first is essentially just sparsity. Excuse the spelling error there. And the second is knowledge distillation. So what I've got at the bottom here is a figure out of a paper on sparse-gated mixture of expert layers. It came out of Google, and it's Jeffrey Hinton and Jeff Dean's paper from 2017. Essentially, this is one of the bigger kind of innovations happening at the moment, is people are finding ways of making little groups of modules or clusters of neurons inside of a neural network layer. And if you're following DeepSeek and like the whole kind of, how they managed to make a small model that could compete with these bigger companies, like this is one of the things they had. They had a mixture of experts layer, and in general, most LLMs now are a mixture of expert models. So what happens is that when information comes into the model at the bottom here, it first goes through this green module, and it's called a gating module. And gating just means it's going to switch on or off regions of this layer. All right. And so I think we've seen a few of those in other architectures already. And so this decides which one or two of these things get switched on. Now, the big innovation of this paper was that it had this huge implicit sparsity to it. Sparsity meaning that a lot of things were set to 0 and only a handful were set to 1. In this case, it was expert 2 and expert n-1 were switched on. Now, that's a hyperparameter that they choose. In this case, they chose 2. And in this case, they just were taking the two most useful experts to use, or two most useful sets of hidden neurons to use in this layer, and you get those two sets of neurons, you get their output, and you add it together, and then that gets forward propagated. And because everything else is 0, it's possible to do this quite efficiently, especially if you kind of code it up with all the neat tricks and architectural things that like kind of come in the architecture and stuff like that, the way of like making sure that you're not loading it into the GPU unless it's necessary or so on, or and Google's doing a whole bunch of federated learning and stuff like that, so that they're distributed and stuff. So there's a lot of very clever engineering aspects to this, but ultimately what this does mean is that you can actually be really, really efficient in how many neurons you're using at any given time. The flip side of this is that usually it can be a little bit wasteful on memory. Again, you have more modules than you need probably for your data set and stuff like that, and you also have this gating module that now needs to learn which modules to choose. And so this like idea of figuring out for a given X, which is the best set of hidden neurons to take responsibility for that X, that's not an easy task for the gating network to do. But it's something that's kind of cool, and it seems to be working really, really well. And it's one of the ways that they're scaling up these modules, these architectures. And the thing that I think is really cool is that this sparsity, and it's called modularity, you kind of form these little modules of neural networks, are coming up in a lot of really cool architectures. So there was one by Bengio in 2019. And in this case, they were using attention. So I'm not going to go through this whole thing. It's called a recurrent independent mechanism for anyone who's interested. Again, the link's at the bottom. But essentially, the whole point is that they were taking in this input and then using an attention-like process to essentially choose how to filter information between network modules, not just where to attend or kind of where to put weight on the input side. They were then almost using it as like this sparse communication layer coming from this attention mechanism. And so there is actually this push towards cool ideas around like, how do you reuse computation, and how do you kind of allow attention to also lead to these kind of recurrent computations over time. Okay, and so this was like a cool idea they had, where attention was guiding the weights going forward, and then whatever module it chose to use was also recurrent over time. And so there was this like very clear bit of memory that you're probably familiar with from the other recurrent networks we've spoken about. And so there's cool ideas of how do you mix attention and recurrence in a way that's really, really beneficial. And again, I think a lot of papers are now starting to build off of this recurrent independent mechanism architecture. So again, I just want to highlight that I think if you are going to go forward in NLP, it's one thing to rely on the fact that these models scale well, particularly because transformers are so parallelizable and have this like very implicit tendency or regularization towards really sophisticated behaviors, like in context learning and stuff like that. But ultimately, there is also a lot of architectural stuff that's currently being baked in that may not be super obvious, but is actually super beneficial. And the big one here is sparsity, right? You want to be using as few neurons as possible at any given time, but then you also want your neurons to be very meaningful. That is called specialization, when a neuron kind of only fills one very interpretable specific role in the network. And again, this leads back to things like mechanistic interpretability. Like, can we identify the role a neuron is playing in an architecture? The second concept of how do we scale neural networks is called knowledge distillation. Again, it's another trick that was used by DeepSeek. In this case, what we'll have is you'll take in your trained data, you'll train it all with the teacher, and it'll just be this big pre-trained model, right? And again, we spoke about pre-training, we spoke about adapters and all that sort of thing. But what's cool that you can do is you get out of the softmax, usually if it's a classification task, of this pre-trained model, you get labels, but you don't get ones and zeros anymore. You get probabilities. It's the model's own prediction based on the input. And that's actually really informative, especially if this is a good, accurate model, those confidence scores are actually really rich information. And so what new kind of approach to distillation has been around since 2015. It was also by Jeff Dean and Jeffrey Hinton and Vinyals. You can then use that far more accurate learning signal and far more precise learning signal, essentially kind of like a bit of a intermediate between regression, to train a much smaller model. And because you're now getting more accurate labels, it's an easier task or a more clear task for a smaller model to work with. And so that then ends up becoming its own predictor. And what the people also do is they kind of force it to sometimes match the hidden layer representations of the bigger model as well. And so you can start to supervise the features at these independent layers, while also training it to just learn the true labels. And so you get these intermediate supervisory signal coming across from the intermediate layers. You get the actual soft labels being the fact that it's now an actual probability over the label space, coming in at the end, and then you're getting the true labels. And so you get this really rich learning signal, which allows you to train a much smaller neural network on it. And so this knowledge distillation has been actually used a lot lately as well to try and kind of distill information into a smaller mixture of expert models. Again, that was the key innovation behind DeepSeek and stuff like that. So that is kind of at least two ideas of how to scale up. So there's this kind of push towards saying things like, well, let's throw more data at it, and you get the benefit of the emergent capabilities of these models. And that's certainly not something we want to throw away, especially if it's doing things like in-context learning. But at the same time, we want to also try and make these modules more meaningful in their own right. And then the last thing I want to mention, so I guess you can obviously tie all those things back a little bit to your project. Again, the project was trying to expose the fact that it's hard to also get a lot of these things out when you don't have tons of data, and it can be a little bit of an interpretability issue, or a little bit of like a scaling issue, in the sense that even if the task is small and the model your training isn't huge, you might still have to train it for really, really long. You might still need to like parallelize it or actually make more attention heads and so on, just to like get that all immersion capability. Unless you're going to then start doing things like using big pre-trained models, or incorporating explicit regularizers. The last thing I then just want to mention is that one of the big problems that I still see kicking around, and which has been spoken about a little bit in this 2024 paper, is the idea of data poisoning. So one of the big risks, if we are saying that we need more and more data, is that the source of most data, or a lot of data on the internet now, is becoming generated, to the point that now we need to start considering, well, what does it mean when generations of generated data start entering the pipeline? That's what this image on the figure on the left here is saying. It says, well, you start with real data on the left and you train a model, but then that also ends up giving you more data. You've kind of sample from the model, and that gives you more data, and then that's used to train another model. And eventually, over generations, the generated data now also starts filtering into the pipeline. And eventually, by an nth generation, you've now got data that is a little bit real, but also has a bunch of generated data that's being incorporated into it. And so this paper was studying what the potential risks might be of this. It was a little bit of an empirical paper. They did some cool theory. And they never really came to a super conclusive answer. They were claiming that this was going to be a really big problem, but there was a degree of stability to it still. But ultimately, what they're saying is that probable events are overestimated by these models, improbable events are underestimated, and that would make sense, right? We know that there is this coherence kind of trade-off that we get, and diversity trade-off that we get. So if these models are always predicting most probable events, there is a finite amount of data that they can actually generate. And then that gets filtered into the model, which now sees that those events that were originally probable as being even more probable. And we know we've identified the societal risks of this on a kind of propagation of misinformation perspective, or propagating the hegemonic viewpoint along. However, it actually turns out that this is a computationally risky thing that is actually going to get in the way of how we scale neural networks going forward, because probable events end up poisoning reality, and so the tails of your distribution shrink over time. And if we start going back to things like, well, saying that, well, maybe the ZIF distribution of language is the reason that we get things like in context learning and induction heads. Well, if we're losing those tails, the ZIF distribution is characterized by an extremely long tail. And so ultimately, if we get those issues, you're going to end up with something like this, where over generations, the probability of particular tokens and the perplexity of the data is just going to start shifting all the way to the left, right? And again, so perplexity in this case is a measure of variability. It's a measure of actual like information richness. And again, this paper, I don't think it was super conclusive because these distributions were shifting slowly. But you can see very clearly that generation zero has this nice kind of Zipfian-ish distribution over here. And then it starts collapsing and moving all the way to the left to the point that now your bulk is sitting at something quite a lot lower. Um, and so the perplexity of the data, the kind of amount of information richness is actually starting to vanish, right? This is, just to mention, this blue is not a zip distribution, obviously. I was kind of like extrapolating there. But in that case, what this means is that because there's a lot of words that are quite highly informative, there that would kind of essentially give you the zip distribution, not to confuse that point. But then ultimately, a lot of this information gets lost, and you see the kind of tail towards the right hand side, this bit over here getting smaller and smaller, and then a lot of just information in this model is getting lost, in which case the neural network can start to, the pressure on the network to be able to handle rare, highly informative words starts vanishing. And this paper called this model collapse, and ultimately they kind of showed that there's good reason to believe that the quality of generations are going to get worse as this goes on. So I think that if we're following the trends of neural scaling laws, compute is going up. We know that, and that seems to be happening stably. Same with the number of parameters, especially if we're looking at things like mixture of expert models and sparsity and distillation. In that case, what we're effectively doing is finding innovative ways to give us more parameters without necessarily the downsides of it, right? And especially that in this, I think, if it's not this paper, it was another one on neural scaling laws, kind of really made it clear that these mixture of expert models is one of the ways that we can start getting into the higher order number of parameters. And so we seem to have good answers on the parameter side as well, through things like giving it kind of sparsity and implicit modules in the network, and really clever attention mechanisms that give you lots of parameters doing very interpretable things, or at least that's if they're working well. But I think dataset size is the thing that's going to catch up first, and especially if the way that dataset size is growing and shifting to the right is through this process of generations of generated data. And so I think that this, if anywhere, there is kind of cool areas to maybe be thinking around impacts to be made. It is certainly in this space around what does generations of generated data mean. And so if anyone wants to chat about that a little bit more, let me know. I have some ideas, but that's beside the point. So I think I'm kind of, again, this was more of like just a broader thing, a last little recap of the most modern ideas, but again, also hopefully tying the bow on your project, which I did just open here. So a lot of the papers that I've referenced here are sitting in these references there. You can see things like in-context learning, mechanistic interpretability, neural scaling laws. So I think this little bit of information here is hopefully was also something that was useful to you while you were doing your project. Especially this idea that like induction heads only really appear with a degree of scale and long trainings. That was kind of something that I think came out pretty clearly in this project. So I hope it was useful, and I hope it was like an interesting project that didn't require tons of compute, but potentially had room for some clever ideas. And I do hope that some of you end up taking NLP further and dealing with some of these more kind of pressing issues like data poisoning and sparsity and modularity and stuff like that. Because again, I think there is a lot of impact to be made here. Anyway, cool. I will post this. Please just make sure you know those little few concepts from this from your project, and then some of what I've spoken about today. Just make sure you know these concepts. But anything about this that like comes up in any of the exams and stuff, it would have been stuff we've spoken about before, and it's also just going to be at quite a high level because obviously we haven't studied this in detail. Cool. All right. Thanks everyone. Good luck for your studying.